The topic of this week's lecture is complex and imaginary numbers. So to see how these arise, if you consider a simple mathematical equation like, say, x squared minus 1 is equal to 0. Now we can rearrange that to say that x squared is equal to 1, so therefore we know that x is equal to the square root of 1, and therefore it's equal to plus or minus 1, because we can multiply plus 1 gives you 1. And also, if we multiply minus 1 by minus 1, it will give you plus 1. Now, suppose we just change that equation a little bit, and instead we have the equation x squared plus 1 is equal to 0. Therefore, now x squared is equal to minus 1. And therefore x is equal to the square root of minus 1. And the problem now is, what's that equal to? Because we know that multiply minus 1 by minus 1, it gives you plus 1. Multiply plus 1 by plus 1, it gives you minus 1. But what number, when you multiply it by itself, will give you minus 1? And the answer is that in the numbers that we've been using so far, what we call real numbers, there isn't any number that can do this. So if you like, what the mathematicians had to dream up is they had to say the number represents this is not a real number, if you like, but it's an imaginary number. So it's an imaginary number, so you could say this is an imaginary number, and to give you the short for that, give the symbol small I. So the square root of minus 1 is equal to I. And of course this carries over into other square roots as well. So say the square root of minus 9. So again, this is what number, when we multiply by itself, will give you minus 9. And in the real number system, you can't think about that. But one way of understanding it based on what we have above is you could say this is the square root of 9 multiplied by the square root of minus 1. So now we can solve that, because we've already said the square root of minus 1 is equal to this I. So the square root of 9 we know is plus or minus 3. So what we say is the square root of minus 9 is equal to plus or minus 3i. So what this development really was is that in addition to the real numbers that we're familiar with, we also have imaginary numbers. And one of the way to understand this is to look at what's called an organ diagram. And an organ diagram simply represents number systems like along what we usually call the x-axis here, the horizontal axis. We call this the real axis system. And this corresponds, here's the 0 point here, this corresponds to all the real numbers that we know, like 5, 10, square root of 9, 2 million, 5.34, minus same numbers on this side. So this is all the numbers, what we call the real numbers. And then on the y-axis, you have an axis here for the imaginary numbers. So the y-axis corresponds to the imaginary numbers. So again, you can grade this out. Here we have our system, kind of like that. And similar for the imaginary part. So one way of thinking about this is that when we're talking about real numbers, we're just talking about this one dimension of this graph. A real number will just have a real part. It doesn't have any imaginary component. In other words, its imaginary components on this imaginary axis is 0. Likewise, a purely imaginary number doesn't have a real part. Its a real part will be 0. Now what you can have though is you can have a number that has a real and an imaginary part, and a number like that you'd represent as, say, these are this is 1, 2, 3, 4, 5. So say we had a number out here. Now this has a number, real part 5, and it has an imaginary part 5 as well. So this is the imaginary, this is a number, and you could represent it as plus 5 plus 5i. Likewise, you could dream another number down here, so it has a real part 4 and imaginary part 2, but now this is going minus 2, so this would be 4 minus 2i. So the imaginary axis again is the I-axis. So when you have this situation here, where you have a number that has got a real part, in this case 4, and an imaginary part, minus 2, you call this combination a complex number. So a complex number has got a real and an imaginary part. And again, you could write a real number is a number that's just got a real part, it hasn't got any imaginary part. In other words, it's got some real number, say 5 here. At this point here is 5 plus 0i. And likewise, this number here on the imaginary axis is 3i plus 0 real part. So a complex number has a real component and an imaginary component. So let's just draw this organ diagram again, because there's a, so here's our imaginary axis, IM, this is the I, and this is our real here, real part, just like we did up above. And say we had a point here on it, and it's got a real and an imaginary part. So let's say this point is x plus iy. So it's got a real part x and an imaginary part y. So like we've done with coordinate geometry before, we can represent that as a line with magnitude from the origin. Our origin is here, or and likewise again, if you're familiar with this now, we mix an angle theta with the real axis. So now if we drop our perpendicular down to the real axis, we form a right angle triangle. And so here's our x, and over here we have our y on the imaginary axis. So we know now, using Pythagoras' theorem, that the cosine of theta is the adjacent over the hypotenuse. So therefore the adjacent is x, so we know we can say x is equal to r cosine of theta. And likewise, we can say that y is equal to r sine of theta. So what we have done now is we said our complex number was x plus I, y. So that's equivalent now, because x, so that's equivalent to r cosine of theta plus I or sine of theta. Take the r outside, and that's r cosine of theta plus I sine of theta. So what we call this is the, down here, this is the polar form of the complex number. So we can also move on to another relationship using this polar form, and that's known as the Euler relationship. Now, Euler was a famous mathematician, and what he showed, and it's a very important equation in mathematics, and it's also highly relevant to chemistry, is that this e to the I, so I is our square root of minus 1, theta, he showed that that's equal to cosine of theta plus I sine of theta. Now, it's easy to show this relationship using what's called a Taylor series. Then you need to remember that e to the I theta is equal to cosine theta plus I sine, and also that e to the minus I theta is equal to cosine of theta minus I sine of theta. So you can also multiply this theta by a constant. So in a more general form, you can show that e to the I k theta, where theta is a constant of some number, is equal to cosine of k theta plus I sine of k theta, or e to the minus I k theta is equal to cosine k theta minus I sine k theta. So of course you can multiply this across by r, so you'll have r e to the, just leaves the I theta, leave the k out for this one, that's equal to r into cosine of theta plus I sine of theta. So of course, if you look back here now, for the polar form of a complex number, we found that we could write the what you call the standard form for a complex number here. We could write that in the polar form as r cosine theta plus I sine theta. So what we can say now is that we can also, of course, the polar form, because of this Euler relationship, can be written as r e to the I theta as well. Okay, so we'll come back to that in a moment. What we can do with real numbers, we can do algebra with real numbers. So we can do the same thing with complex numbers. So if you have addition of complex number, just take a simple example, 6 plus 3i is one complex number, and you want to add that to 8 plus 2i. And all you do is you add the real parts together, so that goes to give you 14, and you add the imaginary parts together, and that'll give you plus 5i. Likewise for subtraction. If you have, again, let's get the same numbers, 6 plus 3i, you multiply, sorry, I'm talking about subtraction, aren't we? So it's 6 plus 3i, so 6 plus 3i, and we're going to subtract 8 plus 2i from that. So again, as you subtract the real parts from each other, so 6 minus 8 will give you minus 2, and you subtract 2i from 3i, and that's going to give you plus 1i, or plus I. Multiplication. Again, so you have 6 plus 3i, and you want to multiply that by another complex number, 8 plus 2i. And again, so you multiply each term exactly as you would do for real numbers. So you get 6 8s, you get 48. Plus 6 by 2i, that's going to give you 12i. 3i by 8i is going to give you 24i. And 3i by 2i is going to give you plus 6i squared. And now, of course, I squared, I is equal to the square root of minus 1. So I squared is equal to minus 1. So if you simplify this up a little bit, you have 48 plus 12i plus 24i, that's going to give you plus 36i. I squared is minus 1, so this will give you minus 6. So your answer is going to be 42 plus 36i. So that's your complex number when you multiply. So again, you need to remember that when you multiply the i's together, you get I squared, and that's equal to minus 1. Next thing we want to talk about is the conjugate. This is quite an important part. So let's suppose we label the complex number z, and that's equal to a very general form x plus iy. So x is some value and y is some value. Now the complex conjugate, and we label that z, and we give a superscript asterisk. So z asterisk, all that is x minus iy. So you just get the negative of the imaginary part. So let's suppose we have, give an example, say z is equal to 3 plus 5i. Then the complex conjugate, again how we notate that, z superscript asterisk is equal to 3 minus 5i. So that should be fairly clear. Let's go to the case where we wrote it in polar form. Now z is equal to our cosine theta plus I sine of theta. Now z asterisk, or the conjugate, complex conjugate in this case, is our same as above theta. And this is the real part, this is the imaginary part, so it's minus I sine of theta. So likewise, remember the Euler relationship. We said that we could write this here as equal to r e to the I theta. Now z asterisk, of course, then is r e to the minus I theta, because that's what this corresponds to here. And we said that e to the I theta is cosine theta plus I sine theta, e to the minus I theta is cosine theta minus I sine theta. So this is a complex number, and this is its complex conjugate. Now, an important property of the complex conjugate is that when you multiply a complex number and its complex conjugate together, you get a real number. You don't get a complex number, you just get a real number. Basically, you don't get any imaginary part. So take an example of that. So you had 3 plus 5i, it's one complex number, and its complex conjugate, of course, is 3 minus 5i. The imaginary part is negative. So now, what you would multiply it as, you get 9, you get minus 15i, you get plus 15i, that multiplication there, and then you multiply that, and you're going to get minus 25i squared. And you can simplify that out. So they cancel out, so you're going to get 9. Now it's minus 25i squared. We know that I squared is equal to minus 1. So it's 9 plus 25. That's equal to 34. It's a real number. It hasn't got an imaginary part. Likewise, if you do the write it in its polar form using the Euler relationship, so we're going to just put the number in k this time. So z, the complex conjugate of that complex number, is r e to the minus I k theta. We've just done that above. Now, if we do z, if we do the multiply that complex number by its complex conjugate, what are you going to get? You're going to get r squared e, and when you multiply two powers, you add the powers. So it's e to the I k theta minus I k theta. And of course that's going to be r squared, this is going to be e, it's going to be 0, because you're expecting the same thing from just the same as this, so it's e to the 0. and e to the 0 is 1, so it's equal to r squared. Let's go by 1, that's equal to r squared. Let's make it quite obvious. So this is important in quantum mechanics in chemistry. So in quantum mechanics, you know that you solve the Schrödinger equation, and the solutions are the wave functions that come out of that, and you usually denote these functions with the Greek letter psi. Now, an important point about quantum mechanics is that you have this wave function here, and in certain cases it can be a complex number. So you may also remember that there's a very famous called the Born relationship, which says that the square, usually it's referred to as the square of the wave function, but actually in proper definition it's the multiplying the wave function by its complex conjugate, and that gives the probability density. So psi by psi asterisk of the complex conjugate gives the probability density. Okay, so key point here is we're talking about the probability density. This has to be a real number. It's about the probability, say, of finding an electron in a certain region, and clearly that can't be any imaginary or complex form. That has to be a real form. So therefore, if your wave function is complex, like it is, and the solutions come out from the Schrödinger equation do come out to be complex numbers for certain systems, then if you multiply that complex number that you get by its complex conjugate, you get a real number, and that will give you the probability density. So if we take an example, a very simple example, what they call a particle on a ring, and you may have covered this in last year's lectures in quantum mechanics, but it's a very simple two-dimensional representation. So you have an electron going around a nucleus, and you can solve the Schrödinger equation exactly for that system, and you get a wave functions, and they're given by the following type of equation: I e to the I n, and usually the angle will denote by the Greek letter phi. So this is a normalization constant n, and m is your quantum number. So you get a number of wave functions depending with different values of m that satisfy the Schrödinger equation, and this is the form of the equation. So that's so n is your normalization constant, and m is the quantum numbers. So to work out the probability for that, we said that you need to multiply psi by its complex conjugate. So psi star. So that will give you the probability density. So psi, this is psi here, then psi, the complex conjugate of that is n e to the minus I m phi. So now, similar to what we did above, if you have psi asterisk is going to be, so you're multiplying that by that, so you're going to get n squared, same as above, e to 0 is equal to n squared, and that's a real number. Okay, so we've that's pretty much what we want to cover in this. You've got lots of examples in the exercises, and so you should go working on them. Now,